By now, we have covered a lot of the modeling aspect of longitudinal data. Specifically, we have learnt about the general linear model for longitudinal data, and then we have extended it marginal modeling as well as the mixed effects modeling of longitudinal data. So, just to recap, the marginal model focuses on the population level effects. So, the focus is more on how the response is related with the covariates, the relationship is of importance, while treating the correlation parameters to be a nuisance, and here the idea is to get to report a consistent estimator. In the mixed effects modeling, we go one step further and try to explicitly model the correlation as well as the relationship between the response and the covariates. The final form of modeling is transition models. Now, transition models differs from marginal model as well as the mixed effects model in the sense that transition models allow the past response to affect the present response. So, it is more like in time series modeling where we have done AR1 structures or ARQ structures, the autoregressive structures, where the present is influenced by the past outcomes. So, if we use this idea in context to a longitudinal data, what we get is the transition model. In this session, we would be briefly describing what is a transition model, and then we would take an example in R to show how to deal with a transition model. A transition model allows the past value to influence the present observation. We all know that longitudinal data are correlated, and this correlation in context to a transition model is explained by incorporating the past values while explaining the present observation. So, we can say that the model explains the correlation by using the dependent structure of the present value on the past value. Now, formally we write that if script eta ij is yi1 to yij minus 1, and this denotes the past responses for subject I, then the transition model for the conditional moments is defined as g of mu ijc, which is nothing but g of yij given the past observations, that is eta ij. So, yij is the present and eta ij is the past, is a linear model of the form xij transpose beta plus kappa r, and then these are known functions. So, these kappa r's are known functions and r runs from 1 to s eta ij alpha beta, and variance of or vijc is nothing but variance of yij given script theta ij, and that is phi v mu ijc, where phi is the dispersion parameter. So, here once again k r are known functions. So, we can think as an example, we can think of the Markov chain. A Markov chain of order q means that the present depends on the past q observations. So, transition models are most useful for equally spaced data, and Markov chains of order q are very effective transition models. Now, let us take specific examples. Let us talk of the, or let us see what is a linear transition model. So, a linear transition model is nothing but a simple autoregressive model of order q equal to 1. So, here what happens, yij is xij transpose beta plus epsilon ij, the normal linear model, but epsilon ij is modeled as alpha epsilon ij minus 1 plus zij, where zij is the white noise process or the random error following IID normal 0 tau square, and then tau square comes out to be sigma square into 1 minus alpha square, where alpha is exponential of minus 5, and that's greater than equal to 0. So in this context, Yij conditional on Yij minus 1 follows normal Xij transpose beta plus alpha Yij minus 1 minus Xij minus 1 transpose beta. So this alpha into Yij minus 1 minus Xij transpose beta, this is what is causing the correlation. So here we are seeing that the jth observation is dependent on the j minus 1th observations, and the variance of this conditional distribution is tau square. So we can safely say that Yij minus 1 is a predictor of Yij, and the marginal covariance structure in this case Yij, Yik comes out to be alpha to the power j minus k, absolute value or difference, absolute difference of j minus k into sigma square, and this is nothing but a AR1 structure. Now if we say what's the marginal mean of this, so expectation of Yij comes out to be Xij transpose beta, just the marginal mean. So beta hat has the marginal model interpretation. Now, so the interpretation of beta hat in the linear transition model is same as that of the marginal model. Now consider an autoregressive model of order q, ARQ. So here what happens? Then Yij would be equal to Xij transpose beta plus R runs from 1 to q, alpha R, Yij minus R minus Xij minus R transpose beta plus Zij, where Zij follows normal 0 tau square. So here the kappa R function is based on the previous responses eta ij through alpha and beta, and that's equal to alpha R Yij minus R minus Xij minus R transpose beta. Now consider a logistic transition model. So previously we dealt with a linear transition model, now consider a logistic transition model. So a first order Markov chain for binary response is log it Pyij equal to 1 given the past responses eta ij is equal to Xij transpose beta plus alpha Yij minus 1. So that means log it Yij equal to 1 depends on the past response, and so here we can say that here because it's a Markov chain of order 1, first order, so we have R equal to 1, so kappa 1 eta ij alpha beta is alpha Yij minus 1. Now to illustrate this we would be talking about a data, and later on we would download the data, so it's and we would run this model in R, but first let's see what the data is all about, and it's called the ICHS data. So what was done was over 3,000 students were medically examined quarterly for 6 visits for vitamin A deficiency. The idea was to assess the vitamin A deficiency and see whether they had suffered from respiratory infection and xerophthalmia. So xerophthalmia is another infection, and xerophthalmia is the infection is caused as a manifestation of vitamin A deficiency, right. So this data is available, and later on I am giving the source of the data, but consider that this is the data, and the probability of a child having a respiratory infection at time Tij depends on infection status at previous visit. So this is a very reasonable assumption that at present if the probability that a child has a respiratory infection is dependent on whether the child had an infection previously or not. So here if we fit the same model as discussed previously, the first order Markov chain, so here exponential alpha is the odds ratio of infection at the previous visit, and exponential of beta is change or beta k. So if I assume that there are k covariates, is change in log odds for a unit change in xk. among children free of infection in the last visit. So, here one thing is to be noted, that here beta k is the change in log odds for a unit change in xk among children free of infection at the last visit. That last visit is important. So, that means here beta is not a marginal effect interpretation as it had for a linear transition model, because for a linear transition model we had that betas have a marginal effect interpretation, but here betas are the change from the last visit. So, if the visits changes, the effect of betas also change, and hence it is not a marginal model or marginal effect interpretation. So, we can see what is the transition probability matrix is like. So, here you see the transition probability matrix comes out to be on the columns we have Yij and on the rows we have Yij minus 1. So, Yij equal to 0 means not infected and Yij equal to 1 means infected, and these are the terms. So, 1 by 1 plus e to the power Xij transpose beta. So, this is the transition probability matrix or the transition probability for Yij minus 1 equal to 0 and Yij equal to 0. And see for 1, this is alpha xi, so it is basically the same, but here it is e to the power xij transpose beta plus alpha. So, if we do the row sum, it comes out to be 1, meaning that this is a TPM or the transition probability matrix, but it depends, you see, the transition probability matrix at any step j depends on the covariate xij, and this can vary from subject to subject, and this is the reason why we cannot say that betas have a marginal interpretation. Now, see that kappa r eta ij alpha beta is alpha r kappa r eta ij. Now, assume that if this is the structure, then g of mu ij is a linear function of both alpha and beta, because this alpha r, yes, so it comes out to be a linear function of beta and alpha, or so estimate. So, the estimation here is similar to GLM, but we can consider that we have an extended set of explanatory variables, because these betas are from the xij's and the alphas come from kappa 1 and kappa 2 and up to kappa s. But assume that kappa r depends on both alpha and beta. For example, in the linear transition model, or if we go by a log linear transition model, that is what we are estimating. So, the conditional estimation is done from the conditional score function. So, assume that kappa r eta ij alpha beta depends on both alpha and beta. Now, this is the situation which comes up for linear transition models as well as for log linear models, log linear transition models. So, here the estimation is done from the conditional score function, and the fitting produces the marginal models, but then that means we are fitting a marginal model with extended explanatory variables, which are the betas for xij, or rather for we get the explanatory variable, the effect of the explanatory variable betas, and that's been included as xij in the model, and then kappa 1 eta ij to kappa s eta ij results in alpha. So, now for a logistic model where alpha and beta, where the linear function, where g mu ij is a linear function of alpha and beta, we can straightforward use the GLM with the past responses as explanatory variables. For the linear and log linear model, where kappa r depends on both alpha and beta and they are not separable in that sense, we use a generalized GEE, generalized estimating equations, with extended explanatory variables, the past responses. So, in both cases, in logistic it is GLM, whereas in Poisson we use here now we would be downloading the xerop data. So this is the same data, the ICHS data that we are talking of, but for xerophthalmia. So, and this can be obtained from the following website that's been given here, that's http faculty.washington.edu Hegarty books analysis longitudinal, and the data is called xerop, so one can download it. I have downloaded it and have saved it here. So and the data is a text file, so here we are using read.table to read in the text file, and the data also has the name, so we are using the column names. And then we first need to create two more data sets to fit the transition model. So we first fit in the data, read in the data, and then what we do is we create infection. So the infection status for lag 1 and infection status for lag 2. So these are the two infection status. So a little bit of reshaping of the data for first and second order transition models, and the age is in months, so we subtract 36 from it. So the details of this model is given in Diggle et al. We are not going to explain it. And here, so we create two data sets, one is xerop 1 and one is xerop 2 for fitting the first order and a second order transition model. And note that because the response is a binomial one, so we would be using a GLM. So at the 0th order, where we have not included what's the effect of the respiratory infection at the previous level, but we have just analyzed whether there is a respiratory infection and whether there is a deficiency of vitamin A, which is being measured by xerophthalmia. So this comes out to be transmod 1, and if we run this, we get transmod 1. So what do we see? We see that xerophthalmia has no effect. Now let's see what is the first order transition model. So here the respinf.lag1 gives us an indicator of whether there was a respiratory infection at the previous instance, and then we apply or rather we adjust for the covariates like age and season 2, and we run this second model called the transmod 2. And when we run the transmod 2, we see that the first order model, so the whether or not there was a respiratory infection in the previous outcome or the previous visit has an effect on whether there is respiratory infection at the present visit or no. So we see that here the p-value is less than 0.01 or sorry 0.1, so the p-value is 0.09, so at 90% it does have an effect. And yes, age and seasons are having significant effects, but xerophthalmia doesn't have an effect. And then we include the second order lag also, so it depends on two previous visits. Whether respiratory infection now depends on two previous visits, and what do we see? We see that if we use a second order lag, then it's not explained well. So here none of the lag is explaining. So we think that the first order model is better, because a first order model or lag of first order explains or rather is significantly affecting whether there is respiratory infection in the child. Yeah. So in today's session we learned about transition modeling. So now we know that if we have a longitudinal data, then based on the situation and based on the design, we can use any one of the three models. If modeling the mean response is of importance, we can go for a marginal model. If modeling the mean response as well as the correlations or modeling the correlations are important, then we can go for a mixed effects model. And finally, if there is reason to believe that the past responses affect the present response, then we can go for the transition models.